All right, let's dive into one of the biggest, most ambitious quests in all of science. We're talking about the search for a single, elegant theory that could explain our entire universe from the tiniest flicker of energy to the cosmic web of galaxies. You know, at the very heart of this search is a question that has kept physicists up at night for decades. What is all of this? Really, what is the fundamental fabric of reality made of? And to even begin to answer that, you first have to understand the giant roadblocks sitting right in the middle of modern physics. So here's the problem. Physics today is kind of a house divided against itself. On one side, you have Einstein's masterpiece, General Relativity. It's beautiful, it's elegant, and it perfectly describes the big stuff: planets, stars, galaxies, the smooth fabric of spacetime. But on the other side, you've got quantum mechanics, the wild, chaotic, probabilistic rules for the super, super small, the world of atoms and particles. Now here's the kicker. Both theories are fantastically successful in their own domains, but they are completely, fundamentally incompatible. They don't just disagree, they don't even speak the same language. Now, whenever you have a deep conflict like this between two of your best theories, it's a huge red flag. It tells you that your understanding of the universe is missing a piece, a big piece. It points to some major gaps in our best rulebook for the particle world, something we call the Standard Model. And when I say gaps, I mean huge, gaping holes. For all its incredible success, the Standard Model just gives up on some of the biggest questions. For starters, it has absolutely nothing to say about gravity. It's also completely clueless about dark matter and dark energy, which, by the way, make up 95% of the known universe. And it offers zero explanation for other deep mysteries, like why fundamental particles seem to come in 3 distinct generations, or why there's any matter in the universe for us to exist at all. So to solve this enormous puzzle, to stitch together the big and the small, physicists knew they needed something completely radical, a brand new idea. And that's where the leading contender comes into play, the incredibly ambitious and kind of wild idea of string theory. The core idea is just stunningly simple and elegant. What if, when you zoom way, way in, past atoms, past protons and electrons, what if the fundamental building blocks of reality aren't little points at all? What if everything is made of tiny, one-dimensional, vibrating strings of energy? In this picture, different vibrations of the same string give rise to different particles. It's like a cosmic guitar string. One note is an electron, another is a photon, another is a graviton. It's all just different music from the same fundamental string. But, and this is a huge but, this beautiful idea comes with a truly mind-bending price of admission. For the mathematics of the theory to work, for the equations to not just fall apart, our universe can't have just the 3 spatial dimensions plus time that we all know and love. No, it needs more. It needs a total of 10, or in some versions, even 11 dimensions. So yeah, that immediately raises a pretty obvious question, right? If there are all these extra dimensions woven into the fabric of reality, well, where are they? Why can't we see them? So if they exist, why aren't we bumping into them all the time? Well, the theory has a fascinating, if strange, answer. The reason we don't see them is because they're compactified. They're curled up so incredibly tightly that they are effectively invisible to us, hidden all around us in plain sight. Okay, the best way to think about this is with the classic garden hose analogy. Imagine you're looking at a long garden hose from really far away. To you, it just looks like a one-dimensional line, right? But if you're a tiny little ant crawling on the surface of that hose, you know better. For you, there's not just the long dimension to walk along, there's also a whole other dimension you can explore, the circular path around the hose's circumference. The idea is that the extra dimensions of string theory are just like that circle. They're curled up on a scale so impossibly small that to our giant scale, they're completely undetectable. So what kind of shape do these tiny, hidden dimensions take? Well, the math suggests they are bundled up into these incredibly complex 6-dimensional geometric shapes called Calabi-Yau manifolds. And these aren't just some abstract mathematical curiosity. If the theory is right, these shapes could be the literal hidden architecture of our reality. And here is where it gets absolutely mind-blowing. The idea is that the specific shape, the geometry of that hidden manifold determines, well, everything about our universe. The precise way it's twisted and folded could set the strengths of forces like electromagnetism. And remember that mystery of why there are 3 generations of matter particles? Well, it turns out the number of holes in the Calabi-Yau manifold could be the exact reason why. It's an idea where geometry is destiny. Now, back in the 1990s, things got a little messy. physicists realized there wasn't just one version of string theory, but 5 different consistent versions. And that kind of defeats the purpose of a single theory of everything, right? This led to an even bigger, more profound idea, a theory that could unite them all. And that grand, overarching framework is called M-theory. You can think of it as the mother of all string theories. It's this proposed 11-dimensional theory that shows how those 5 different string theories weren't really different theories at all. They were just different ways of looking at the same, single, underlying reality. It's our most complete and powerful version of the idea so far. So at this point, we have this absolutely beautiful, mathematically powerful, all-encompassing theory. It's elegant. It's compelling. There's just one enormous problem. In science, a theory is only as good as its ability to be tested. And this right here is where string theory hits a massive, massive brick wall. And you don't have to take my word for it. Even one of its most important architects, Edward Witten, puts it plainly. For all its mathematical beauty, string theory hasn't made a single concrete prediction that we can go out and test with an experiment. And until it does, it remains a hypothesis, not established physics. So the first huge challenge is what physicists call the landscape problem. You see, it turns out there isn't just one possible shape for those extra dimensions to be curled up in. Not even close. There are a lot of them. How many? The current estimates are somewhere around 10 to the power of 500. That is a 1 with 500 zeros after it. A number so staggeringly large, it's basically impossible to comprehend. Each one of those possible shapes would create a universe with its own unique laws of physics. So trying to find the one specific shape that describes our universe in that near infinite sea of possibilities is, well, it's an unimaginable task. But okay, let's say we could solve that. There's an even more fundamental problem. To actually see a string, or to directly probe these extra dimensions, you would need to concentrate an absolutely insane amount of energy into a tiny point in space. And this really puts the problem into perspective. The amount of energy we can generate with our most powerful machine ever built, the Large Hadron Collider, is just nothing compared to what we need. The energy required to see strings is millions of billions of times greater. We're not even in the same ballpark. It's an energy scale that is just completely, utterly beyond our reach. Now, this doesn't mean everyone's just given up. Of course not. If you can't see something directly, you look for its fingerprints. So scientists are hunting for indirect clues. They're looking for things like exotic new particles predicted by related ideas, or maybe faint, telltale signatures left over in the afterglow of the Big Bang, or even subtle hints hidden in gravitational waves from colliding black holes. And that really brings us to the core dilemma of this whole quest. We've got this incredible theory, a mathematically solid framework that could, potentially, explain everything we see. But it describes a level of reality that is, for now, locked away from us, sitting just beyond the reach of our experiments. And that leaves us with this profound, almost philosophical question that's shaping the future of physics. What is science, really? When our most powerful and promising ideas about the universe outpace our ability to actually go out and test them. It's a huge challenge, and how we answer it will define the next chapter and our amazing journey to understand the cosmos.